AI Neural Network. Introduction. An AI neural network is a computational model inspired by the way human brains work. It consists of layers of interconnected nodes that process data. Types of neural networks. Feedforward neural networks. Data moves in one direction, no cycles or loops. Convolutional neural networks, best for image processing, utilizing convolutional layers to capture spatial hierarchies. Recurrent neural networks, ideal for sequential data, with connections that loop back to maintain context. Transformers, highly effective for natural language processing tasks, using self-attention mechanisms to process data in parallel. Generative Adversarial Networks, comprise two networks that work against each other to generate new data samples. Key components of neural network. Structure. Neural networks typically have an input layer, one or more hidden layers, and an output layer. Each layer consists of nodes that perform calculations. Training. Neural networks learn by adjusting the weights of connections between nodes based on the input data and the error of their predictions. This process is often done using a method called backpropagation. Activation functions. Each node uses an activation function to determine its output. Common functions include sigmoid, ReLU, and tan. Applications. Neural networks are used in various fields, such as image and speech recognition, natural language processing, and game playing. Structure of neural network. 1. Neurons, basic units that process input. Each neuron receives input, applies a weight, sums it up, and passes it through an activation function. 2. Layers. Input layer, receives the initial data. Hidden layers, intermediate layers where processing occurs. More hidden layers can capture more complex patterns. Output layer, produces the final prediction or classification. 3. Weights and biases. Connections between neurons have weights that determine the influence of one neuron on another. Biases are added to the weighted sum to allow the model to fit the data better. Training. 1. Forward pass. Data flows from the input layer through hidden layers to the output layer, producing predictions. 2. Loss calculation. A loss function measures how well the model's predictions align with actual outcomes. Common loss functions include mean squared error, used for regression tasks. Cross-entropy loss, used for classification tasks. 3. Backward pass. The network adjusts weights and biases to minimize the loss. This involves calculating gradients of the loss with respect to each weight. Updating weights using optimization algorithms like stochastic gradient descent or ADAM. Applications. 1. Computer vision, image classification, object detection, and facial recognition. 2. Natural language processing, language translation, sentiment analysis, and text generation. 3. Healthcare, disease prediction, medical image analysis, and personalized medicine. 4. Autonomous systems, robotics and self-driving cars, where perception and decision-making are crucial. 5. Result prediction, laboratory analysis. Challenges. 1. Overfitting. The model learns noise rather than general patterns, leading to poor performance on unseen data. Techniques like regularization and dropout are used to mitigate this. 2. Interpretability. Understanding why a neural network makes certain decisions can be difficult, making it challenging to trust AI in critical applications. 3. Data dependency. Neural networks often require large datasets for effective training, which can be a barrier in some fields. Future directions. Research continues to make neural networks more efficient, interpretable, and capable of learning from less data. There's also a growing interest in combining neural networks with other AI methods, such as symbolic reasoning. Example. Here we are going to make the neural network for lab data analysis. I have a data set that I found on the internet and we are going to produce similar results from our neural network using Python. See the data set link from the description. Python libraries you need: NumPy, Matplotlib, Pandas, Keras, Statistics, TensorFlow. Here are the 106 data that I extracted from the research paper. We are going to produce the same result as the paper. Find the research paper link in the description. They researched to predict the effects of operational parameters on the dissolution of copper, molybdenum and rhenium from molybdenite concentrate through mesoacidophilic bioleaching. The initial pH, solid concentration, inoculum percent and time were used as inputs to the network. The outputs of the models included the percent of copper, molybdenum and rhenium recovered. They found that maximum copper, molybdenum, and rhenium recoveries were to be obtained on the 30th day, with values as high as 72.99%, 2.83%, and 27.17%, respectively. Here I have developed a code for finding the high-accuracy neural network models for copper, molybdenum, and rhenium recoveries separately. I feed datasets twice into the network because I have only 106 datasets, which is not enough to feed the neural network. Then I separated data into 3 sets that needed to feed 3 models. I used RNN for training the model with the relo activation function with the 4 layers with 5-5-2-1 sequence for the copper model. Then I introduced the AdaMax as an optimizer, losses made from Keras. Here I commented on code that provides the visual representation of the model. I used that to have an idea of the model that I developed. Then I calculated the accuracy of the model with the real dataset by comparing the result with the real result. If the accuracy is higher than the previous model, it will be saved as a new model while saving the accuracy of the model into a CSV file. I developed a different neural network for molybdenum as well as rhenium with different sequences. Here I am running the code for a few times so I can have a best fitted model for each. Then it will print the accurate models for recoveries. Let's run the code. Here you can see code will have 20,000 epochs with the 913 batch size per model. The code will check the loss of the model and calculate the accuracy of the model. Then the network adjusts the weight and the bias of the model to minimize the loss of the predictions. Here you can see code has generated a few neural networks separately with high accuracy. This CSV file provided the accuracy of the copper RNN model so I could choose the best model easily. Here is the accuracy of the molybdenum RNN model and the rhenium RNN model. Let's choose the best RNNs for our project. Here I have developed a code to read our RNNs. So let's see. Here, I have introduced the best models by renaming the models as CU model MSC, MO model MSC, remodel MSC. Then, I loaded the original dataset and converted it into standard data using Sklearn. You can load the copper model into the code using the Keras library. Mention part of the code visualize the maximum recovery of copper and the difference between predicted data with the real data of copper recovery. I did the same thing for the other 2 models. Here is the best part. I have developed the code to generate and calculate the recovery of these metals so you can have a result without lab equipment and chemicals. Let's run the code. Here you can see the deviation between the real value with the predicted value and the error. Here the maximum recovery of our copper is 67.91 plus 1.97% with a model accuracy of 97.92% and the real value is 72.99%. Maximum recovery of molybdenum is 2.71 plus 0.05% with a model accuracy of 99.55% and the real value is 2.83%. Maximum recovery of rhenium is 27.25 plus 1.04% with model accuracy of 97.92% and the real value is 27.17%. We nearly got there, but running the code for a few more times will produce a highly accurate model for our purpose. Here you can see the network structure of each model as well as a visual representation of the network model. Let's do some calculations. Here is the result. Here it says type pH value between 1.46 to 2.14 because we train the network using this range. If we enter a value which is out of this range, the model will overfit. Therefore, we need to stay between in range. After a few adjustments, you can use this model as your lab data analyzer.